Hey Math 8, this is Mr. Bainey, and we're going to take a look at, hey, what's up Math 1? We're going to take, hello, this is Mr. Bainey. Let's take a look at lesson 19.2, Transversals and Parallel Lines. In this lesson, we're going to be looking at angle relationships when we have the two parallel lines cut with a transversal, and that's a new vocabulary word. In the last lesson, recall that we learned about two angle relationships, but those angle relationships are when we have just two intersecting lines. So let me show you what that means here on this picture. I'm on the first page, and we learned about these four angles right here. So these four angles are created when the line T right here and line P intersect. Angle 1 and angle 2 are right next to each other. They're adjacent angles, and they would be supplementary. Angle 1 and 4 would be supplementary. Angle 2 and 3 are supplementary, and so are angle 3 and angle 4. So that's the first type of angle relationship. You could also say they're a linear pair. That's also true. But the end result is they're supplementary, which means they add up to 180 degrees. Now, if I took angle 1 related to angle 3, those would be the same exact measure, and those are called vertical angles when they're across from each other like that. Angle 2 and angle 4 are also across from each other. Now let's take a look at the angle relationships you're going to learn about in this lesson. There's four of them. So we have corresponding angles, and over here on the right side is an example of a pair of corresponding angles. Then we have same side interior angles, alternate interior angles, and alternate exterior angles. And I'm going to talk about these more in depth as we go through the postulates and theorems that you'll see in this lesson. One thing that needs to happen in all of our statements for the rest of this lesson is that two lines need to be parallel, right? So we don't get the results that we want, the results that are interesting, unless the lines are parallel. Over to the right, you're going to see a picture of two lines. They look parallel, and they are in fact parallel because of these two arrow-looking things that are in the middle of the line. That's notation on a picture to show that those two lines are in fact parallel. If I drew something like a parallelogram, which has two pairs of parallel sides, to show that they're parallel, I would put the arrow on the segment, and then if I have another pair, I would use 2, just like that. Remember that this notation doesn't mean that the lines are congruent, the segments, sorry. So they're not congruent, they're just parallel when they have those arrows. And then this symbol right here kind of looks like two L's put together. That is a parallel statement. So that statement says that line L is parallel to line M. And you'll want to look for that notation or the parallel statement in some of the problems you're going to come across in this lesson and also in the rest of this unit. On this next page, you come across our first postulate, and this is for same side interior angles. The statement reads, if two parallel lines are cut by a transversal. And I apologize, I didn't even say what a transversal was, but this statement, you're going to see this at the beginning of every statement, like postulate or theorem, in this whole lesson. That means that it's important that we have two parallel lines. Now, the transversal is just a line that intersects two other lines. So in this diagram, and then if you even look on the first page, right, the line T is the transversal because T is intersecting this one and also this line Q right here. That's what makes it a transversal. When the two parallel lines are intersected by our transversal, the pairs of same side interior angles are supplementary. And we have already talked about what supplementary means. They're going to add up to 180 degrees. So what's important here is that we're able to identify what same side interior angles are and how we can find them in the picture. So I'm going to use this diagram here, and we're just going to identify where they are, but then I'll mention how exactly you find them. Especially if your picture looks a little bit different, you'll just want to know what to look for. Same side is kind of obvious in terms of just regular English, but same side is referring to our transversal. So same side of the transversal means here's our transversal. Angles 1, 4, 5, and 8 are all on the same side. They're on the left. And then 2, 3, 6, and 7 are all on the same side. They're on the right. Interior is referring to inside of our parallel lines. So if you took the parallel lines and let's say we just closed it up, meaning I make it like this, kind of like a box like this. Interior, or means inside, is the angles 3, 4, 5, and 6. Those are interior. So which ones are on the same side of the transversal, but also inside of our parallel lines? Okay, and remember, we're looking at pairs of angles. So those pairs are angle 4 and angle 5. Now remember what this statement says. It says that they are supplementary. So I'm going to write a full statement here. The measure of angle 4 plus the measure of angle 5 is equal to 180 degrees. All right, we know that only when the lines are parallel. And our other pair of same side interior angles is angle 3 and angle 6. So those add up to 180 degrees. Okay, we'll get to a problem, probably something from your assignment. They don't give you a whole lot of your turns, practice problems here where you're dealing with actual angle measures. So we'll get to it probably after we go through some of these other theorems. On the next page is the alternate interior angles theorem. And this is called a theorem, whereas the last one was a postulate, because remember that theorems, we can actually prove that theorems are true. A postulate, we don't prove that that's true. It works like a definition. We just accept that definitions are true, just like we're going to accept that the postulate is true all the time. Theorems, you can question it, but I can prove it to you. And we're going to do the actual proof of this theorem down below, and this is the only proof that we'll do just so you can get some more exposure. But let's identify how we look for alternate interior angles. So interior is the word we've just seen, and it means exactly the same thing as the same side interior. Interior is the angles that are inside. So if I, again, kind of close up these parallel lines, the angles 3, 4, 5, and 6 are still inside. And alternate now, it's pretty much the opposite of same side. I'm no longer going from, or staying on the left side or staying on the right side. We're going to go angle 4, which is right here. And then on the opposite side, right? Alternate means like kind of switching sides or opposite. It's angle 6 right here, angle 4 and angle 6, right? And you know what? I didn't even read the statement above to you, but when the lines are parallel, our result is the alternate interior angles, they're going to be the same measure. Let's write the statements for these angles. So alternate interior would be the measure of angle 4 is going to equal the measure of angle 6, because those are alternate interior angles. Measure of angle 3 would equal the measure of angle 5. Let's go ahead and prove this theorem is actually true. When we prove a theorem, and it's written like an if-then statement, this is just a reminder, I mentioned this in another lesson, that the if part of the statement is your given. So if something is true, then the prove is the then part. Pairs of alternate interior angles will have the same measure. So you'll see here in our setup of our proof that we're given that the two lines are parallel. We want to prove that the two measures, right, of the alternate interior angles, angle 3 and angle 5, we have it down right here. We want to prove that they're equal, okay? So we have that picture, we have our given, and we have our answer, right, where we want to end up. This one actually helps you out with giving you a bank of reasons to use, and they already have the statements all filled in for us. So I'm going to kind of go back and forth to the proof and back up to our picture. So our first statement says that line P is parallel to line Q, and that's our given, right? There's no other reason than that's just what we start with. The second statement says that angle 3 and angle 6 are supplementary. So taking a look at the picture, angle 3 and angle 6, those are same side interior because they're both on the right side of the transversal. They're inside of our parallel lines. So they're supplementary because of the same side interior angles postulate. So I'm just going to write down same side interior. That's enough to show me that you actually know that relationship. So statement number 3 says that they add up to 180 degrees. That's just definition of supplementary, right? So if you say they're supplementary, then definition says that they add up to 180 degrees. So it's definition of supplementary angles, but I'm just going to write definition of supplementary. Statement number 4 says that angle 5 and angle 6 form a linear pair. They are a linear pair. And if you look at the picture shows that they actually look like a linear pair because they're right next to each other. So here's angle 5 and angle 6. Linear pair because they share a side. They form this straight line right here. So it just looks like a linear pair. So I'm going to say that it is by definition of a linear pair. That's why we can make that statement. Right? Remember, when you're coming up with the reason, you have your statement. You just ask the question, why can I make this statement? Why can I say that angle 5 and angle 6 are a linear pair? Well, it's because they look like they're a linear pair. Statement 5, they're supplementary, angle 5 and angle 6. That is by the linear pair postulate. The linear pair postulate just says linear pairs are supplementary. So if you don't remember that it's a postulate, if you just write down linear pairs are supplementary, that's mainly the reason because, or that's the reason why we can make this statement. Next statement is angle 5 and angle 6. The measures will add up to 180 degrees. That's by definition of supplementary because the statement before said they are supplementary. So we know they're going to add up to 180. Statement 7. This is a long proof. I know. Statement 7 then has this long equation. So let's try to figure out where this is coming from. Measure of angle 3 plus measure of angle 6 equals measure of angle 5 plus the measure of angle 6. When you see something like that, especially when you didn't come up with that statement, you want to look at the previous statements and see where it came from. So there's the measure of angle 3 and the measure of angle 6. And then there's the measure, whoops, that's not right there. Measure of angle 5 plus the measure of angle 6. Look at what they're both equal to. That's equal to 180, that's equal to 180. And therefore, the two things I boxed, they're equal to each other. And we can make that statement because it looks like we use substitution. The full reason is substitution property of equality. You'll see that up here above the proof. But I'm fine if you just put substitution. And then to make statement 8, measure of angle 3 is equal to the measure of angle 5. Think about how we got here. Why can I say that these two are equal from this statement, right? Or sometimes you might have to look at other ones, but it's from this statement. Well, if we subtract measure of angle 6, since the measure of angle 6 is on both sides, that would be gone. And that leaves the measure of angle 3 is equal to the measure of angle 5. So the reason we can state number 8 is because of the subtraction property of equality. And I'm just going to write subtraction here, not the whole thing. And that's sufficient. And this is the proof, right? For this proof, Notice we didn't use the alternate interior angles theorem in our reasons because we're trying to prove that theorem, just like we wouldn't use a word in its own definition, right? If I'm trying to define supplementary, I don't use the word supplementary in a definition. And I'm allowed to use any definition, any postulate, any property that came before this theorem. So everything you've learned before this, you can use, right? We're going to be learning some more postulates and theorems in the future. Obviously, we can't use any of those yet. And our last theorem, there should be one more here, and I'm gonna mention it in a moment. But this theorem is the corresponding angles theorem. Starts out by saying if two parallel lines are cut by a transversal, right, same thing as the others, then the pairs of corresponding angles will have the same measure. So same measure again, just like the alternate interior angles. Let's look at how we would get corresponding angles. So corresponding, you want to look for, I'm actually going to move this to the other side. You're going to look for one of the angles in this group of four, right here, angles 1, 2, 3, and 4, and then one of the angles here at the bottom. So we're going to match them up. And corresponding kind of means the same thing. We're going to match up or correspond one angle to another. If you remember back in, I believe it was 18.3, whereas corresponding parts of congruent figures are congruent. That's the CPCFC. So same idea here, except we're not looking at different figures. We're looking at different groups of angles. So angle 1 matches up with angle 5. Notice angle 1 is like in the same corner as angle 5. This is the top left, this is the top left. And they have the same measure. Measure of angle 1 equals the measure of angle 5. If I go right below that, angle 4 down here, angle 4, the bottom left, will match up with where it's the same corner as angle 8. So measure of angle 4 equals the measure of angle 8. Okay, think about where our other pairs of corresponding angles are. We have measure of angle 2 and 6. And finally, measure of angle 3 and 7. So we have a ton of pairs of corresponding angles, and that's the end result. The fourth statement we should get in this lesson is the alternate exterior angles. The theorem that's just on the previous page, the alternate interior angles theorem, if you just change interior to exterior, pretty much the same thing. So we're going to be looking outside of our parallel lines this time, because exterior means outside. So here's my parallel lines. I'm going to close this off. Our exterior angles are angles 1, 2, and 7, 8. Alternate means they're not going to be on the same side, and they're going to have the same measure. Just like alternate interior angles, that's angle 1 and angle 7, right? Angle 1 is on the left, angle 7 is on the right. And then our other pair of alternate exterior angles is angle 2 and angle 8. I'm going to actually go through a couple of your problems from the, not from the assignment that I'm giving you, but some that are just in this practice section. So number 1 on page 950, anytime you're given two angles, you want to automatically think what's the relationship between those two. And then we can figure out, are they going to be equal? Are they going to be supplementary? Or maybe we don't know enough information yet. So let's look at our diagram here on the right side. We have line M, line N. This looks a little bit different than the other ones we've seen, but you still have your parallel lines. We still have our transversals going across here, left and right. And it tells us that they're parallel, lines M and N, right? This is our parallel statement. We're going to match the A, B, C, and D with the relationship, pair relationship. So angle 4 and angle 6, I'm going to mark those here, angle 4 and then angle 6. Those are inside of our parallel lines right here. Here's our parallel lines. It's inside. And then our transversals right here, they're both on the bottom of the transversal. So that would be same side interior angles. Okay. And next, angle 5 and angle 8. Here's angle 5, here's angle 8. Angle 5 and angle 8 are in the same group here, right? So that means you're going to be using the angle relationships from last lesson. Angle 5 and angle 8 are across from each other, and that makes them vertical angles. Okay, otherwise, if they're right next to each other, they're adjacent, that would be supplementary angles. All right, remember that same side interior angles. Let me go back to part A. Those are going to add up to 180 degrees. Vertical angles will have the same measure. They'll be equal measures. Let's look at our next one. Angle 2 and angle 6 is this one and this one. Those look like they match up. They're both the bottom left corner of the group of 4 angles. And that means matches up here. And process of elimination looks like the last one's alternate interior, but let's just verify that. Angle 4 and angle 5. Looks like they're both interior, right? They're inside of our parallel lines. Angle 4 is on the bottom, and then angle 5 is on top of the transversal. So yes, it is alternate interior. And all the problems on this next page are going to ask you to find the measure of an angle. But again, I want you to think, what's the angle relationship? So I'm going to do number 3, and more than likely I assigned that one to you, but I'm going to go through it because I want to be clear on what I'm looking for. So we want to know, what does the measure of angle 5 equal? Well, look at 4 and 5 in our picture on the right. Angle 4 and 5 looks like they're same side interior angles. So I want you to identify it, write it down even. Same side interior. That's the relationship. Okay. Now there is a same side interior angles postulate. The postulate says they're going to add up to 180 degrees. So if one of them is 82 degrees, we subtract that from 180 and we will get the measure of the other one, which is 98 degrees. And that's it. We've identified the angle relationship and then we figured out our measure, right? Get in the habit of doing that for all of these problems that I assigned you in this lesson. Okay, that's gonna be it. Thanks for watching. Have a great day.